All right, we are about to go on a wild journey. We're going to start with something you can literally hold in your hand and zoom all the way down to a scale so tiny it builds, well, everything, our entire reality. It's a trip deep inside the stuff that makes up our world. So, yeah, let's get right into it. Okay, I know what you're thinking. That's a weird question, right? I mean, one is a delicious lunch, and the other is this kind of bizarre rainbow-colored crystalline metal. But trust me, by the end of this, you are going to see how they're connected in the most fundamental way possible. It all comes down to how scientists start sorting out the very stuff of the universe. So imagine you have to make sense of, well, everything, all the stuff in the world. Where do you even begin? Well, you start by sorting it. And the first, biggest category for almost everything we run into is something called a mixture. And honestly, the world is just full of mixtures. A mixture is just a substance made by physically mashing two or more things together that aren't actually chemically bonded. You know, your taco? It's got lettuce, meat, cheese. That's a mixture. Spaghetti sauce, tomatoes, herbs, all mixed up. Even that sports drink is just a simple mix of water, sugar, and some flavorings. And yeah, even mixtures themselves get broken down into two types. So on the left, you've got what we call heterogeneous mixtures. Just think of a pizza or that taco, right? You can see all the different parts. You could literally pick them out. But then on the right, you have homogeneous mixtures. These are the ones that look completely the same all the way through. Like salt and water. You can't see the individual salt bits floating around, can you? It all just looks like one thing. So here's the absolute key takeaway. In any mixture, the ingredients are just physically hanging out together. It's like they're in the same room, but they haven't actually gotten married, you know? There's no deep chemical change. And that is so important because it means you can, with a little effort, pull them apart again. They are not locked together forever. Okay, so it's one thing to say you can separate them, but how do you actually do it? How does that work in the real world? Well, let's take a look at a really simple experiment. So just imagine you've got a beaker with this stuff all jumbled together. The whole goal here was to figure out exactly how much salt was hiding in that initial 12.50 gram sample. And to do it, the student just did something pretty clever. They added water, which dissolves the salt, and then they just filtered out all the solid stuff, the sand and the gravel. And this is what they ended up with. After separating everything else out and then just evaporating away the water, boom, they were left with 3.65 grams of pure salt. They literally pulled one part cleanly out of the original mixture. And that right there perfectly illustrates the whole idea of what a mixture is. All right, so if you keep separating mixtures and separating, what do you eventually get down to? You get to a point where you can't separate it anymore by physical means. You get down to what scientists call pure substances. But hold on, we are not done sorting just yet. Think of it like peeling an onion. We've peeled back that first big layer, the mixtures, and now we've found these pure substances. But guess what? Even this category gets divided up again. So on the one hand, we've got elements. These are the real, true fundamentals. Think back to that block of bismuth we talked about. It is made of nothing but bismuth atoms, and that's it. Then, on the other hand, you've got compounds. Things like carbon dioxide or baking soda. Now, they're still pure because every single little particle is identical to the next, but each one of those particles is actually made of different atoms that are chemically bonded, like properly stuck together. And this right here, this is the bedrock. An element is as simple as matter gets. You cannot do a chemical reaction to break bismuth down into anything simpler. It just is what it is. It's like one of the basic single-color Lego bricks in the ultimate Lego set of the universe. But what really is an element when you get right down to it? What makes bismuth, bismuth, and not, say, gold? To answer that, we have to zoom in. I mean, way, way, way in. We are now going inside a single atom. Okay, so here it is. This is a basic model of what an atom looks like. You can see that dense little center there. That's called the nucleus. And then you have these even smaller particles kind of orbiting around it. Every single element, from the oxygen we're breathing right now to the metal inside your phone, is made up of these tiny, tiny structures. So let's break this down even further. Inside that dense little center, the nucleus, you've got positively charged particles called protons and neutral ones with no charge called neutrons, all packed in there together. And then, whizzing around on the outside, you have these negatively charged electrons. And that's it.
Seriously, just those 3 tiny particles are responsible for building literally everything.
But here's the thing. The number and the arrangement of these 3 particles, it's not random at all. It's a code. You could even call it a secret code that defines what an element is, what it does, and how it's going to behave.
So that leads us to the big question, right? You can have different numbers of all 3 of these particles, but which one of them is the non-negotiable ID card? Which one particle, if you change it, changes the very soul of the atom?
And there's your answer. It is the proton. This is the single most important rule in all of chemistry, probably. The number of protons is an atom's fingerprint. It's its social security number. It is its identity. It dictates absolutely everything. And this number, the number of protons, has a special name. We call it the atomic number. And it's an ironclad rule. An atom with 1 proton is always hydrogen, an atom with 6 protons is always carbon, an atom with 79 protons is always gold. There are no exceptions. Ever.
Okay, so let's jump back to that model atom we were just looking at. If you remember, its nucleus was labeled with 8p+. Well, that p+ stands for protons. So that means this atom has exactly 8 of them.
And if it has 8 protons, that means its atomic number is 8. And any atom anywhere in the entire universe with an atomic number of 8 is, by definition, an atom of oxygen, every single time. That's the code, that's the rule.
You know, this table is a perfect little puzzle to see all these rules in action. So let's look at that first one, manganese, Mn. Okay, it has 25 protons, so what does that mean? Its atomic number has to be 25. And since it's neutral, the number of electrons has to match, so that's 25 too. Simple. Now look at gold, Au. Here, we're given the atomic number is 79. Well, that instantly tells us it has 79 protons, and since it's neutral, 79 electrons. And the mass number? That's just the protons and neutrons added together. But then look at the last one, calcium. It has 20 protons, but only 18 electrons. That 2-electron difference is what gives it that little 2+ positive charge.
So let's just put it all together, nice and neat. Protons are sacred. You don't mess with the protons because they define the element's identity. But the other 2 particles, they can vary. Change the number of electrons, and you just get a charged particle called an ion. Change the number of neutrons, and all you do is change the atom's mass. The element itself stays exactly the same.
And that brings us right back to the beginning, full circle. We started with a messy mixture like a taco, and we journeyed all the way down to the protons, neutrons, and electrons that build it. Everything you see, the taco, the bismuth, the television, it's all made from the exact same 3 tiny particles, just arranged in different ways. It kind of makes you wonder, doesn't it? If we know what the ingredients are, what are the instructions? What are the fundamental rules that tell these particles how to build an entire universe?